Hey guys, today we're going to fill in our parent functions library in your notes packet. You can find this on page 35 and page 36. Okay, so there are 8 major functions that we're going to cover, and parent functions, remember, are the characteristics that give each graph its own shape, right? So this is kind of the deciding factor of what shape it takes. And of course, we add in transformations to stretch, shrink, move it around, even flip it over and do some creative stuff with the shape of that graph. Okay, so these characteristics are kind of the baseline. And from here, we're going to work our way to transforming our graph to look in different shapes. Okay, so the first function I'm going to talk about is the constant function. And the way I'm kind of going through this video, I'm going to start by drawing the graph of the constant function, and then I want you guys to pause, and anything that you can fill in that right-hand section, domain range, whether it's even, odd, neither, anything you can get from that graph, go ahead and fill that in, and then you can see my answers, and I will kind of give some commentary on those. Okay, so let's start by drawing this constant function. Now, constant, I wrote that the equation is y equals b, and y equals b is just that it equals a flat number. So a constant is just a horizontal line, and it goes off infinitely in both directions, okay? So anything that you can come up with for that domain and range, go ahead and do. Okay, so let's fill in some information about this. The constant function is kind of the simplest, but in its own way, kind of a weird function because y is just equal to a single number. In this case, I called that number b, and it could be any number, 2, 3, it could have been negative even. Okay, now this graph stretches from left to right infinitely, so my domain, all real numbers are negative infinity, positive infinity. The range, however, is only one number, so I kind of want to mark that's kind of an interesting thing. It could be whatever number we chose. So bracket 2 bracket, if we were just saying y equals 2. This function is even. You can fold it over straight across itself across that y-axis. And remember, even and y-axis symmetry are the same thing. Those are going to always go together. Okay. This function never increases, never decreases. It's always constant. And I did want to mention that there is a y-intercept at 0b, okay, whatever the number is, but it's not really the intercepts we care about. We really care more about zeros and x-intercepts. Okay, so I just wanted to go ahead and mention that. So those are the details for the constant function. Let's look at our next function. Our next function, we're talking about the linear function, and you can see I wrote my equation as y equals x. Remember, you could also say f of x equals x. That's the same as saying y equals. All right, so this graph looks to go straight through the origin, right? Everybody knows what this line is. It's going up this way and down through that origin, right? Slope of 1. Okay, anything you can think about with this graph, let's go ahead and fill in that chart. So take a second, try to fill it in yourself. Okay, so here's the information for your linear function. Not a whole lot to say here, okay? Domain and range go from negative infinity to positive infinity. This function is odd, okay? It's always increasing and never decreases. And the intercept that's kind of the key one is at 0, 0, the origin, okay? You can see again, odd and origin symmetry are going to go together. Those both are the same thing. All right, those always have to go together, okay? And there's no min or max on this graph. Let's keep moving on. Okay, let's look at the quadratic function. Everybody's favorite. You guys already know what this graph looks like. It's going to make a U shape, and we call that a parabola, right? So again, try to fill in anything you can on that right-hand side yourself, and then we can fill in the rest together. Okay, looking at the quadratic, we can see there are some interesting points here. Our domain is still all real numbers, but our range is a little different than we're used to. Since my graph actually does have a low value, it cuts off at 0, we can see my range starts from 0 and goes to infinity. And I wrote it two different ways. I said 0 to infinity or y is greater than or equal to 0. Okay, now this graph is even, or this function is even, and this graph has y-axis symmetry. Again, those two go together. The trick is even describes the function and y-axis describes the graph, but they always have to go together. They're kind of partners. Increasing from 0 to infinity, okay, that's the right-hand side of my graph, and I'll go ahead and highlight that in red just to show you that. And you can see, hey, that's the increasing section, it's trending upwards. The yellow section is coming downwards, right? In the middle, my graph turns around, okay? You can see we have a minimum value for this graph as well, okay? So that's kind of the details for the quadratic function. So the next one we have up is going to be our cubic function. Okay, so the cubic function is y equals x cubed, or f of x equals x cubed, and our graph is going to kind of curve up this way and curve down the other way. And mine is not the smoothest looking thing here, but usually it is kind of a smooth curve. And see how much you can fill in on this. Okay, so as you can see, my domain is again all real numbers stretching from left to right, negative infinity, positive infinity. This function is odd, okay, which means it has origin symmetry, right? The right side is the opposite of the left side, right? They are negatives of one another, okay? No minimum or maximum, no decreasing sections. The whole graph continues to increase at all times, okay? Let's take a look at our next function. Okay, this is kind of an interesting one, the absolute value function, right? You might remember this makes an interesting V shape, okay? And these both have the same slope and kind of follow the same numbers on each side. See what you can fill in for that domain and range. One interesting point that you might note about this is a lot of this information looks very similar to the quadratics graph. And if you look back at your quadratic function, you're going to notice, hey, these actually do look similar, even though this is straight lines, whereas the quadratic makes a curved U shape, this makes a hard V. Okay, they still have some very similar features in that they increase and decrease in the same areas. They have similar ranges and domains, right? They're both considered to be even, and they have that y-axis symmetry and a minimum value at 0, 0, the origin. Okay, the square root function, okay? So this one is a little different than the ones we've seen before, okay? Let's see what that graph looks like. This graph starts from the origin and kind of has this like slow, mopey looking curve, okay? And it's kind of like that quadratic turned sideways. All right, let's see what we can come up with for this one. Okay, some key features here. This graph is really interesting because both its domain and range only go from 0 to infinity. Okay, it does not have any negative values either as a domain or range, which is completely different than anything we've seen so far. Okay, my graph, since it's cut off, can't really have any symmetry. Okay, it starts from 0 and goes forward, so there's no symmetry, and it always increases from 0 to infinity. So you'll notice that's actually matching up with the domain perfectly. No sections decreasing. There is that intercept at 0, 0, the origin. And again, like we said, no symmetry. And there is a minimum at 0, 0. The square root function is really interesting because of that cutoff, right? Remember, we can't take the square root of a negative number, and that's why this graph only starts from 0 and moves forward from there. Okay, let's take a look at the reciprocal function. And this is another really interesting one, and you may need your calculator to remind you what this looks like. But if you graph this, you would see it splits your graph into two sections, like this and like this. So in between those, we can actually kind of sketch in some little imaginary lines that you may remember from previous lessons. These are our asymptotes, and remember that means our graph isn't going to really hit these lines, so we should be very careful about that, okay? All right, so let's take a second, see what we can fill in here. This function is going to be a little different than the ones we've seen so far. Okay, so as we look at this kind of, you'll see our domain and range both are the same, but they are a very interesting setup. We go from negative infinity until 0, and from 0 until infinity. And I have to actually note that x can't be 0, and that u in the middle, when you see 0 parentheses u 0, right? That's showing you that, hey, I stopped at 0 and then I skipped 0. 0 is not included, okay? And kind of very simply, we can state that with just x does not equal 0, which I find a little bit easier to say than from negative infinity to 0, 0 to infinity. And the range looks very similar, you can see that. This function is odd. These sides do mirror each other perfectly as positives and negatives, okay? Now this function always decreases. Something that's kind of cool and unique to it, a lot of people don't realize, is the left-hand side is always going towards negative infinity, so always getting smaller. And the right-hand side starts out high, but it's going to keep going down towards 0, so it's also decreasing. You can see the symmetry and how there is no minimum or maximum value for this function. All right, and our last function in this library is our newcomer on the block. And this is a function that you probably just learned about, and it's called the greatest integer function, or the stair function is the kind of the slang term for it. And remember, that's the function that kind of makes these stair-step looking pieces, right, going onwards each time. And we have to remember it's always filled in at the left side and open on the right side. Okay, and it makes these little stair pieces, and we can kind of continue with that same trend down the other way. And again, what this does is it takes your number and it always basically says, what was the integer that you just passed, right? The greatest integer that is not as high as this number. And basically that means just round your number down. So if you have 1.5, that's going to round down to 1. If you have 0.5, that's going to round down to 0. If you have negative 0.5, that rounds down to -1. So just watch out for those negatives. They're a little bit tricky, okay? Now, this one has an interesting domain and range. Give it a shot, see what you think, and then look at our answers. Okay, so here we are talking about that greatest integer function, and you can see my domain's actually all real numbers again. It really does hit every number, even though there are these jumps in the graph where the stair is, it still has an answer for every x value. But the range, now that's kind of interesting. You can see that I wrote this double stroke z, which represents all integers that exist, right? And remember, back to elementary school when we learned that integers are basically just whole numbers. You could also write it with this long set and say, hey, it's dot, 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 and show kind of, hey, this is a trend that we're seeing. But I think the double stroke z is kind of the best bet, showing you that, hey, this is all integers. All right. Now, this function has no symmetry and is not even or odd. Okay. This set of intercepts is every number between 0 and all the way up to 1. Once you hit 1, it's not an intercept anymore. Okay. So this is actually any number where x is between 0 and 1. So I'm just going to write it as x is less than 1, but greater than or equal to 0. Okay? And there's no symmetry and no minimum or maximum for this graph. Okay, so that's the last function we've really talked about here. And each of these functions gives your graphs their own shapes. So any quadratic graph is always going to make a parabola, and every stair graph is always going to have some kind of stair shape. Now, it could be wider, shorter, shrunk, or moved up and down, could even be flipped over, but it can't change the fundamental shape because that's what it gets from its parents. Okay, all right, that's it for the parent functions. Make sure that you have all this information down, and happy studying.